Welcome to the next part of our video tutorial series on the pneumatic motor. After we successfully assembled the motor in the last video, it is now time to set it in motion. In this video, you will learn useful features such as editing components directly within an assembly, using component colors for better clarity, and the ability to review your design with sections, measurements, and a collision check. In addition, we will show you how to bring the pneumatic motor to life with a motion study to make its function visible. Let's not waste any time and get started right away. Before we set the pneumatic motor in motion, let's check if we assembled everything correctly. For this, we use the collision check in the check menu. Select the interference command. With this tool, we can examine individual components to determine if they overlap and could cause problems during assembly. Since we want to examine the entire compressed air motor, we simply select the entire construction by clicking on compressed air motor in the browser. Then we start the calculation by clicking the icon next to compute. Fusion now shows us a list of all intersections. Additionally, these points are marked in color on the design, so we can find them more easily. In our case, we see that only screw connections overlap. This is normal in the display in Fusion and doesn't pose a problem. To ensure we haven't missed anything, we close the list and start the collision check again. This time, we disregard all screws and standard parts. To do this, we select all other components by selecting the base plate in the browser, holding down the Shift key, and then marking the cylinder head plate. Now check the box for Include Coincident Faces and click Compute again. Now all surfaces that are coincident, meaning they lie directly on top of each other, are shown to us. In the column Volume beacon, however, we can see that none of these connections have an overlapping volume. This means that your construction is error-free. If your pneumatic motor has a collision, don't worry. Check which component connection it is and edit the corresponding joint connection using the previous video. To finally get the pneumatic motor moving, we use the rotary joint between the motor block and the cam. First, we make all the joints visible by clicking on the eye next to the folder joints. Then we open the folder and look for the rotation joint between the engine block and the curve. We now want to rotate this joint 360 degrees to simulate a complete movement. For this, we use the Motion Study command in the Assemble drop-down menu. Our previously selected joint is displayed on the right side with a starting angle of 0 degrees. In the left area, we see a timeline with 100 steps. For a complete rotation, we add a new point at step 100 and set the angle to 360 degrees. If the point was not placed all the way to the right, you can in the line step. Set it to 100 to catch the last point of the movement. After confirming the angle, hold the black slider and drag it across the timeline to check the movement sequence. If the movement is completely and smoothly simulated, set the mode to repeat and press the start button. The speed of the movement can be adjusted using the speed control. To recognize the movement more clearly, we can make the motor block invisible by clicking on the eye next to the component in the browser. This way, we can see how all the parts move together. After completing the motion study, it can be found anytime in the browser under the new folder Motion Studies. Well done. Now we can simulate the operation movement of our motor at any time. To introduce you to some more exciting features in Fusion that can help you work with assemblies, we start with the Function Show Component Colors. Especially with more complex assemblies, it can be difficult to keep track of all components. Fusion offers a practical solution here. Each component can be displayed in its own color. To do this, we click on the command Show Component Colors in the Inspect menu. Now we see all components in different colors, which are also displayed in the browser next to the respective parts. This way, The individual parts can be quickly and easily assigned. You can also activate and deactivate this function at any time by pressing the Shift key and the N key simultaneously. Another helpful option in assemblies is the use of sectional views. With this, we can closely examine the interior of our pneumatic motor. For this, we select the Command Section Analysis in the Inspect menu. To view the center of the motor, we choose the YZ plane as the cutting surface and confirm. Now we see the entire pneumatic motor in section. It becomes particularly interesting to play the movement of the motor in combination with the sectional view. To do this, we open the previously created motion study by right-clicking on it in the browser and selecting the option Edit. With this combination, for example, the stroke of the piston can be determined. To measure the piston stroke, we start with the topmost point of the piston. To do this, we move the timeline of the motion study to step 0 and confirm. We start the command measure by selecting it in the menu Check and measure the distance between the piston and the cylinder head plate. At the highest point, the distance is 1.5 millimeters. Then we edit the motion study again and move the timeline to step 50, the lowest point of the piston. We confirm the motion study and start the measuring tool again to measure the distance. This time the distance is 17.5 millimeters. Perfect. With that, we know that our piston has a stroke of 16 millimeters. We can show or hide our section view at any time. To do this, we click the eye icon next to the section in the Analysis folder in the browser. If you notice an error in a component you designed while viewing the assembled pneumatic motor, that's no problem. Changes to components can be made directly within the assembly. We demonstrate this by adjusting the outer radius of our base plate. To do this, we search for the base plate in the browser and start direct editing with a click on the pencil next to the component. At this point, you again have the option to restore the original position. We realize that we are no longer working in the assembly because the workspace is surrounded by a blue frame, and all other components are grayed out in both the workspace and the browser. We also now see the history of the base plate instead of the assembly in the timeline. Now we can adjust the curves by selecting the fillet in the design history with a double click. We change the radius to 15 millimeters, for example, and confirm the entry. The base plate adjusts accordingly immediately. To undo the change, we press the Ctrl and Z keys, and the radius is reset to 10 millimeters. To finish editing the component, we click on End Direct Edit at the top in the middle. This way, you can make changes to your components at any time without leaving the assembly. Very well done. You have learned how to check your design using collision checks, measurements, and section views. You now know how to make changes to individual components directly within the assembly. You also learned how to simulate the movement of parts through a motion study. In the next tutorial, we will show you how to create an assembly video using animations. Have fun exploring further.